Welcome to Data Science with EJD. In this video, like I promised, we are talking about Markov decision processes. Of course, still talking about reinforcement learning in general, right? The goal is to understand the mathematical framework behind reinforcement learning by studying Markov decision processes in depth with practical Python code to solidify the concepts. All right. So first of all, what is an MDP? So, like I said, a decision process, MDP, is a formal model for sequential decision making. In our last video, we already saw that reinforcement learning is about sequential decision making, some kind of trial and error thing to maximize the rewards attached. So, an MDP describes how an agent interacts with an environment, how outcomes evolve probabilistically, how rewards are accumulated over time. The formal definition is this: an MDP is defined by a tuple. We have M. So a tuple is like if you have two, right? If you have two things, you say it's a double, right? Or a pair. So if it's three, you say it's a triple, right? So a tuple M, which combines S, A, P, R, and gamma, where S is finite set of states, so you have some states, and then A is finite set of actions, so you have some actions. Then you have P of S prime slash S comma A. That's transition probability. That's probability of landing in state S prime when taking action A in state S. So if you're in state S, you take action A, you find yourself in state S prime. That's the transition probability. And then you have R of S comma A. That's your reward function. That is expected immediate reward after taking action A in state S. And then gamma in 0 comma 1. Usually it's hard to get to one, so and that's why in the previous video you have it's an so it's the interval is closed down and it is open up, but here we have a closed interval. It's not supposed to be, it is supposed to be a half open, half closed, half open interval. So and that talks about the discount factor, meaning that the discount factor is from 0 to some value close to 1. So it weighs immediate versus future rewards. Then you have the Markov property now. So the Markov property, we're talking about Markov decision processes. So the future is independent of the past, given the present. So we have probability that you get to state S of t plus 1, given that you have taken actions AT at ST, action AT minus 1 at ST minus 1, that you've taken all previous actions, the probability that you be at the current state. So, and that is equal to probability that you are at S of t plus 1, given that you have taken action AT at state ST. That's the Markov property. Okay, so that this current situation is determined by your previous action. So some key component now we talk about the state. That's all possible configurations, all like in the snake game, all possible movements you can make to eat the food. That's your state. And then of course, in the case of robots, all the possible movements. So example with robots grid world, that's each cell on a grid. Then talking about the action, those are the choices available to the agent. So like anyone who is playing the snake game, you can move up, you can move down, you can move left or right, or even in the robot grid world, that's also true. So transition probability, that's the probability that you are going, if you take that action, you're going to move to a particular S prime. So that's probability of moving to state S prime when taking action A in state S. So for the robot grid world now, the robot may slip. So there's 80% in the other direction and 20% sideways. Then reward, you have a scalar feedback. So that's +1 for goal, -1 for trap, and 0 elsewhere. It's just like, so it's more like for the snake game, +1 if you eat the food, -1 if you don't eat the food, and 0 if you just keep moving around without getting the food. So the discount factor gamma, that's the importance of future reward. So usually gamma is like 0.9. And that's why we say gamma is between it's from 0 to something almost close to 1, but not exactly 1. That's why 1 is not included in the interval normally. So you talk about the policies and value functions now. So if you have a policy pi, so we know a policy tells the agent how to act. A policy basically maps an action, a state to an action. So in this state, what action should I take? And that's basically what it is mathematically here. So pi of A given S is equal to probability of A given S, right? policy A given S or something like that. So what is the action? What action should I take given the state I am in? Something like that. So it is deterministic. Always choose the same action. So if it is deterministic, right, always choose the same action for a given state. If it is stochastic, so this defines the probability distribution over actions. Okay. Then you talk about the state function v raised to power pi. So that's the expected return or cumulative discounted reward starting from state S under policy pi. So you have v raised to power pi of S, and that is equal to expected pi of RT given ST equals S. And that's expected value, expected is of pi, summation from k equals 0 to infinity of y raised to power k RT. We've seen this before in the previous video. Then we have the action value function, that's q raised to power pi. So that's the expected return starting from state S, taking action A, and then following policy pi. So that's q raised to power q pi of S comma A. That's the expected, just like we said, expected return starting from state S, right? Taking action A. Then we talk about the Bellman equations. The Bellman equations relate the value of a state to the values of its possible next state. So what is the value of this state with respect the value of a state, right? So the values of its possible next state. So you have the state value, which is v raised by pi of S is summation over all the possible actions, then pi of A given S, pi of the action given S, all of that multiplied by the reward of S comma A plus the what's that gamma is what's gamma again? Gamma is discount factor, yeah. Gamma is discount factor. So into all of these things. And then you have the action value following a similar pattern. Not exactly, but something close. So you have reward and you have the discount factor and all of that going like that. Then you also have the Bellman optimality equation. So if acting optimally, beyond this V, now this V is the general state, but for optimality, you have V star of S instead of just V pi of S. So these are all the possibilities, but this is the best state you can have. That's the optimality equation. So that's the maximum action you can take, for the reward based on the state and action plus the discount factor multiplied by summation of all the possible summation of all the possible of this new state. So probability of the new state given the action taken at the previous state multiplied by the optimal action at the new state. And for Q values, you have this expression also. So the question is, how do you solve an MDP? Solving an MDP is the same thing as finding an optimal policy pi star that maximizes expected return. So the key methods would include this. So you have policy evaluation. Here, you are computing V pi for a fixed policy. Then you have policy improvement. So improve policy by choosing better actions. Then you have policy iteration. So this alternates evaluation and improvement until convergence. And you have value iteration. So this is a faster method that directly approximates V star. That's the optimal the optimal action, so to speak. Now, let's look at a Python implementation of this now. Python implementation, we want to use the FrozenLake example. So let's code policy iteration on FrozenLake. Okay, I think it's nice to know something about the FrozenLake thing. FrozenLake. FrozenLake. QLearn, yeah. So QLearn for train an AI to solve the FrozenLake environments. So the goal of this article is to teach an AI how to solve the FrozenLake environment using reinforcement learning. So that's the kind of thing we basically want to do here. So in this case, we have the gym thing from OpenAI. OpenAI has a gym, not gym in that sense. Like it's actually an open source thing where reinforcement learning algorithms are compared, basically. So here I want to code policy iteration on FrozenLake, right? So the first thing you want to do, of course, it's always nice to know to have the line numbers showing for easy referencing. So the first thing is install and import. So since you are dealing with Gym for the first time, we have always used NumPy. But I mean, if it's your first time, you can do that. Pip install Gym NumPy. So I already did that before, so it's okay. So then you go ahead and import Gym, and then you import NumPy as NP. So based on GitHub, right, Gym is now becoming Gymnasium in full. So there's a reason why there's been a transition from Gym to Gymnasium. But you can as well just import Gymnasium as Gym. for short, right? So the next thing is you want to create the environment. So you have the environment that's gym.make. You want to make FrozenLake V1 like it's more like a slippery lake. Of course, working on a frozen lake is a big problem, right? So that's the kind of environment you're creating. So it is deterministic. So we are doing it, making it deterministic for clarity. Then you have end states, so environment dot observation space n. Then you have n actions, environment dot action. So the gamma is 0.9. Gamma is the discount factor now. So as close to 1 as possible. So by this, we create the environment. In my curiosity, I just want to visualize what the environment looks like. Okay, nothing serious, just some story. Okay, that's fine. So we have that. Then the next thing is you want to initialize policy and value. So the policy is NP1. So you're creating a matrix of ones where you have n states, comma, n actions divided by n actions. So you can have uniform random, and then V is NP. You are creating zeros of the n state. So some kind of initialization right here. And then we move on to the policy. We move on to the, so, of course, this is the policy and this is the value now. And then we move on to the policy evaluation. So here we create a Python function. Of course, when you see def, you're creating a Python function. Def policy evaluation, which takes these parameters: policy, environment, gamma 0.9 theta, 1 times 10 raised per minus 8 in short. So these are fixed values now. These are default values, except you now state other ones later. So V is n zeros, n with observation underscore space dot n, while true, delta is 0 for S in range, whatever range you have, a V is 0. So for A, which is action problem, and you are enumerating that's now the policy for S. For probability S underscore reward done in this environment, so you have V is plus. So this is incremental. So you have V plus or plus equals action probability times reward plus gamma, all the maths you've been doing so far. And then you have the delta. So you see the delta started with 0. So now the delta is updated there with maximum of whatever delta you have, the absolute value of V minus VS, where VS is equal to V. So you have that updating. So you keep doing that until V is returned. So you return V at the end of the day. Okay, the curious me also wants to see what the V looks like here. Okay, V is all zeros here, Okay, so we have that. Then the next thing is you want to improve the policy. So policy improvements, you define policy improvement, V environment gamma 0.99, policy, the NP dot zeros, of course, zero is a function to populate a matrix with zeros from numpy. So you have that environment dot observation underscore space dot n, comma, environment dot action underscore space dot n. So for S in range, environment dot observation dot space dot n, Q, all these things we've talked about before, being coded. So we do that too. So we have the return policy. So the next thing we want to do is the policy iteration loop, right? So for the policy iteration loop, we now want to get the optimal value function and optimal policy. Those are our goals, at the end of the day. So if you run that, you get all this possible optimal value function. So optimal value function, that's talking about the Bellman optimality equation, that V star S and Q star S. These are the Q values now. So here now you get the optimal policy, you do the policy iteration, you get the optimal value function. So these are the optimal value functions now. So you have a 4x4 kind of thing. You can see the values are mostly close to 1. In fact, we have a particular one here that is 1, and we have some zeros, which talks about losing. Then you have the optimal policy 0, 1, 0, 0, 0, 0, 1, 0. Now, what do these actually mean? That's the issue. So that's why I copied them here for clearer explanation. So for the optimal value function, this is one row, this is another row. I think they are in 4 rows like that. 1, 2, 3, 4. Okay, maybe just go straight, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you have 16 like that. So this is a vector with one value per state. So there are 16 states, e.g., you can have a 4x4 grid. So each value represents the maximum expected discounted reward. So each value you see is the maximum expected discounted reward achievable from that state following the optimal policy. Higher values mean states closer to or leading to the goal state. So all the 0.9 stuff you're seeing, all the one, means that they are leading to the actual state you desire. They are getting the right result, so to speak. Then the values of zero indicate terminal states or holes or pits where the episode ends with no future reward. So if you have all these zeros now, it talks about states where you are losing the game. You're not eating the food, or maybe you are eating the food and maybe you are hitting a barrier, or the snake is biting itself. Then the maximum value here is 1.0, just like you see, which is likely the goal state. Then you also have values close to 1, e.g. 0.99, 0.9801, all these things you see, 0.9703. This indicates state very near the goal where the expected reward is nearly the maximum. So it's at 1, you get the maximum reward. Close to 1, you get some reward. Close to 1 also. So the slight differences are due to the discount factor gamma, which is less than 1, meaning rewards further away are worth less. Now, talking about this optimal policy now, so no, you can see these are 4 different states. Now, of course, in Python, you count from 0. So state 0, 1, 2, 3, right? Anywhere you see 1, that's the approved thing happening right there. So you see, for the first one where you have 0, 1, 0, 0, it means this is state 0, right? That's more like state 1 technically, because counting starts from 0 in Python. So here, action 1 is chosen. So in the next one, in state 1, action 2 is chosen. In state 2, action 1 is chosen. In state 3, action 3 is chosen. So we have all of that. In state 15, in state 14, which is technically 15, action 2 is chosen. So wherever you see 1, that's the action that is chosen. So each row corresponds to a state. The one hot code vector indicates the optimal action to take in that state. So the optimal action to take in this state is 0, 1, 0, 0. That's what that means. So for example, in state 0 now, the best action is the second action, index 1. So the second action is to be taken. That's action 1 based on Python numbering. So this policy maximizes the expected discounted reward starting from each state. Okay. So in summary, you see that the optimal value function tells you how good each state is if you act optimally. So if you act optimally, it tells you how good each state is, all the 0.9 stuff you're getting, or if you get 0. So if you act optimally, then yeah, there's going to be some kind of loss at some point where you have all those zeros. And the optimal policy, all these all these states now. This is a matrix with shape 16 by 4. There are 16 states and 4 possible actions, each likely up, right, down, left, like that, depending on what situation you're in. So the optimal policy tells you what to do, which action to take at each state to achieve that maximum value. So if you want to, so what it simply means is that if you want to get a payoff, so to speak, a maximum expected discounted reward of 0.9509, blah, 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 like this, then it means that you want to go for the second action, which is first action here based on Python counting, right? So for the last state, right, it means you should go for the first action. So if you want to get oh, okay, 0, okay, maybe you don't want 0. If you want to get this one, that's second to the last. So it means you have to go for action 2, or that's the third action normally, but second action Pythonically, so to speak. All right. So again, the optimal value function tells you how good each state is if you act optimally. The optimal policy tells you what to do, which action to take at each state to achieve the maximum value. 0 values in the value function indicate terminal or losing states. All right. Then value close to 1 indicates states near the goal. Then the policy is deterministic, 1 action per state, and tells the agent exactly how to navigate toward the goal. Of course, that won't always be the case because most things in life are actually are not deterministic. They're actually stochastic. They have some level of chance attached to them. Key takeaways: Markov decision processes model sequential decision making under uncertainty, and you see the more reason why it should be stochastic for the most part. Bellman equations recursively define value and optimality. Then policy iteration and value iteration solve MDPs exactly if you know the environment. Q-learning and deep RL, deep reinforcement learning are approximate methods when P and R are unknown. We are going to learn more about this in future videos. Then for next steps now, you can try with slippery FrozenLake, which we've tried already. So here, we tried, we did for the FrozenLake thing. So we did is slippery is false. So if you turn it to true, so yeah, it means you are doing you are making this stochastic. So it won't be deterministic like this one now. So if I make it true, no, it's no longer deterministic, it's now stochastic. So I run again. So it's like, okay, I run that, and then okay, let me try to do this now. So run this, go again, go, 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 go. So you can see the values are now different. They are not like all these 0.9 things we got before, because now we are talking about stochasticity. Um it's not deterministic any longer. So how do you set it to be deterministic? You make a slippery will be false. If you want it to be stochastic, a slippery will be true. So I do this again and I run the whole thing. So this is the deterministic thing we worked with before now. Okay. So that's how, okay, it's still running. Okay, yeah, we have that now. So we're back there. So it is deterministic now. Okay, so we can make it deterministic just like we said there. So by setting it's true, it's slippery to true, it's stochastic to false, it's deterministic. Implement, of course, stochastic is slippery means is a frozen lake slippery? Normally a frozen lake would be slippery, right? So stochasticity is more realistic in this situation. So you implement Q learning for model free learning, all right? Then you can explore deep Q networks, DQN for large state spaces. I think we should talk about this in future videos. So in references, you have Sutton and Barto. I think they wrote the paper on reinforcement learning. They wrote an introduction to reinforcement learning based on the idea of behavioral psychology. And then the OpenAI gym, just click on this, it takes you there. Or if this is not happening, you just type it straight, OpenAI gym, and then it takes you right there. All right. So it takes you to the GitHub, the documentation for it. So it tells you that this is a toolkit for developing and comparing reinforcement learning algorithms, right? So the team that has been maintaining the gym since 2021 has moved all feature development to Gymnasium. So they now have a new place called Gymnasium. So still this. So it's an API standard for single agent reinforcement learning environment with popular reference environments and related utilities. So it was formerly Gym. So in future you use Gymnasium, not Gym. But of course you can install Gymnasium and then import Gymnasium as Gym to keep things short. So with that, we come to the end of this interesting video about Markov decision processes for reinforcement learning. Okay, so let me know how helpful this video is for you. And there's something you like to try that you like me to try out, tell me, let me know. And of course, be sure to subscribe to the channel if you haven't done that already. Finally, we have hit 1,000 subscribers. I want to go for the next goal of 100,000 subscribers. So I know it's a matter of time. When this channel started, like seriously, I had just like 7 subscribers. So thank you so much. If you are one of those subscribers who has made it up to this point. We keep learning together. There's still a whole lot to learn. Share with your friends, share with your children that are in school. You have all kinds of videos on different aspects of mathematics, data science, and things like this, data analysis, SQL, and everything. So please, scholarship talks, everything on the channel. So be sure to subscribe and hit the notification bell so you can always get alerted each time a new video is released. Then, of course, you can become a member of the channel. Just click on join and you see different levels of membership and the perks attached. Then another sweet thing is you can download my code sheets and my data sets and even the slides I use. So you can actually set up your own your system so you can follow step by step. So as I do something, you do it too. So because there's a joy you get when you see that what I'm doing, you can also do it from your end and it's working. So that can really help you. So from the first video, I think on data analysis with Python and even scientific computing with Python, you can see how to set up the whole thing, how to set up a Jupyter notebook from Anaconda and all of that, right? So avail yourself of all of these things and you'll be very glad you did. Um, be sure to like and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing data right. Bye.